Chapter 8 has 3 sections. First section is confidence intervals for a population mean using normal distribution. The second section is confidence interval for population mean using a student t-distribution. Okay, that's a new distribution that we haven't talked about yet. And then the last section is a confidence interval for a different parameter. Rather than mean, it's the population proportion. So we'll start off with looking at confidence intervals for a population mean using the normal distribution. So our goal here is to create this confidence interval, this interval estimate of the population mean. And we're going to start with our point estimate, x bar, that we calculate from sample values. So if you've gone through and done the first part of the collaborate activity, and hopefully you go back to it and see as your classmates add in their means, you can see that I've put in the true population mean. I do know that because the population is only 51. And so you can compare your sample mean and the other sample means, and you'll notice that none of those sample means are equal to the population mean, and all of the sample means that are inputted are not, they're all different. They're all unique. Okay, so each one of those sample means can be used as an estimate of the population mean, even though they're not equal, even though they don't equal that population mean. So we just want to notice that at this point. Okay, so we want to do inferential statistics now. So we're taking those point estimates, those sample mean values, and we want to go through the process of adding some kind of probability, some kind of measure of reliability, so that we have confidence in our estimate. So to do that, we create a confidence interval, and it is going to be centered at x bar, the sample mean. And when we say interval, what we want to think of is an interval of values going from some lower bound value up to an upper bound value. So we represent that interval like this, where we have parentheses, we have one value, then another, and then a comma, and then another value. So the lower bound is just some value, okay, that's less than the mean, and the upper bound is some value that's greater than the mean, okay, and the mean I mean there is sample mean. Okay, the bounds, the lower and upper bound, are going to be based on two different things. One is a chosen confidence level, all right, which is the probability that the interval includes the true mean, mu. Okay, so we can choose this probability. We can choose how confident we want to be. Typically, the values that are used are 90%, 95%, and 99%, with 95 being the most common. Okay, so we can choose what we want. So that's one thing that determines what that lower bound and upper bound is. Now, the other thing it is dependent on is the standard error of the mean. If you remember from the central limit theorem chapter, that standard error of the mean is just basically the standard deviation of x bar, okay, which is this. Okay, so the standard error of the mean is equal to sigma over square root n, or it's the standard deviation of x bar, okay, which we also used this notation to stand for. Okay, so those two things are what determines the lower and upper bound of a confidence interval. Okay, we're saying if we have a 95% confidence level, what that implies, if we write this down in probability notation, what that implies is that the probability that the lower bound is less than mu, the true population mean, is less than the upper bound, that probability is equal to 0.95. Okay, so if we take the lower and upper bound of the confidence interval, okay, the probability that the true mean is between those is equal to whatever confidence level we choose. So we're assuming we have a 95% confidence level. So this would be the probability statement for that. So we want to figure out a way to calculate the lower bound and upper bound such that this statement, this probability statement is true. And then in doing so, that's going to give us a way to calculate the confidence interval. So we're going to make some assumptions, and these aren't too far of a stretch. These are things we know, things that we've established so far. First of all, assume that x bar is normal or approximately normal, and its mean is mu, and its standard deviation is sigma over square root n. Right, that's based on central limit theorem, what we did in the last chapter. And then we're just assuming that we can calculate z, standard normal value, by taking x bar minus mu over sigma over square root n. All right, that's just our calculation for a z-score for a sample mean. And then we assume that z is that standard normal with mean 0 and standard deviation of 1. Okay, so to start this off, we're going to start off with what we know about z, the standard normal. Okay, let's find a particular value of z, we'll call it z sub 0, such that the probability that negative z sub 0 is less than z sub 0 is 0.95. So if I'll look at that on the density curve. If this is our z density curve, okay, we are wanting to have these c values such that the area in between, all right, is 0.95 is that area. All right, so if we look that up on our probability tool, okay, which maybe you can go test that out if you want, we're going to find that that z value is 1.96. Okay, so the negative 1 is then negative 1.96. We can rewrite that probability statement now using those values instead of the z sub 0. So this becomes the probability that negative 1.96 is less than z is less than positive 1.96 is equal to 0.95. Okay. Now, keeping in mind that our goal is to have mu in there instead of z, we are going to, for the next step, we are going to replace z with what it's equal to. Okay, and it's equal to x bar minus mu over sigma divided by the square root n. So we can now rewrite that probability statement, just replacing z with what it's equal to. X bar minus mu over sigma divided by the square root of n less than 1.96 is equal to 0.95. Okay, so all we've done there is just make this replacement, right? Okay, we now have mu in there. So we want mu to be by itself between two quantities, two values. Okay, so we need to do some algebra. So we see that mu is in the numerator and it's got a denominator. So if we if we multiply all three pieces of that inequality by that denominator, All right, we'll clear the denominator in the middle. So this is going to become the probability of, okay, we multiply negative 1.96 times sigma over square root n. So we get negative 1.96 times sigma over square root n less than, if we multiply that middle piece by sigma over square root n, it's just going to cancel out. So we just are left with x bar minus mu. And then multiplying the 1.96 by that quantity, we're going to get 1.96 times sigma over square root n, and then that probability is still equal to 0.95. All right, so a couple more steps here. We've got mu here. We want to get this by itself, okay? So it has an x bar there. So we need to subtract x bar from all three parts. So it's probability. If we take minus x bar minus 1.96, and then we still have the sigma over square root n. Okay, and then if we subtract x bar from the middle, we're going to be left with a negative mu. And then that's less than, subtract x bar, and then it's plus 1.96 sigma over square root n. And that probability is still 0.95. Okay, one more thing here. We want just mu. We don't want that negative out in front. So we multiply all three pieces by a negative. So we're going to end up with the probability of positive x bar plus 1.96 times sigma over square root n. All right, now maybe you're remembering is when you have an inequality and you multiply by a negative, you flip or you reverse the inequality. So this becomes a greater than. If we multiply negative mu by a negative, we get our positive mu. And then we have another inequality. We're multiplying by a negative, so we reverse that. And then that becomes positive x bar and then minus 1.96 times sigma over square root n. And that probability still equals 0.95. Okay, one more thing. We've got our inequalities kind of going in reverse order. And you also see that what we have here is we have x bar, and the first number we have, we're adding something to it, so that's going to be the larger number. And then the second one, we're subtracting something, so that's going to be the smaller number. So we want to flip what's inside there around. So what we end up with is the probability of, we'll go x bar minus 1.96 times sigma over square root n. Okay, so if we flip everything, that means we flip the inequalities, so then that becomes less than mu, which is less than x bar plus 1.96 times sigma over square root n. And that equals 0.95. Okay, so maybe you're seeing that we have achieved our goal. All right, we have this probability statement. We've got mu in the middle all by itself, which is what we wanted. And we've got a value, a quantity to the left of it. All right, that x bar minus 1.96 times sigma over square root n. That is the lower bound. Okay, and the x bar plus 1.96 times sigma over square root n is the upper bound. So here's where we ended up. We have this probability statement. The confidence interval, though, is the lower bound to the upper bound. So when we're actually wanting to write down the confidence interval, we don't have to write down that probability statement. We just write down the lower bound. All right, we have an open parentheses, the lower bound, comma, and then the upper bound. Okay, so we pick those out of the probability statement. So when we say a 95% confidence interval, though, it is implying that the probability that mu is between those two values is 95%. Now, another way that we can write that, a little shorthand, is if we just take x bar and we subtract it and add it, we get the two values. So we can write that as shorthand, x bar plus or minus. So when we have the plus or minus there together, we're saying we want to do both of those things. And it's 1.96 times sigma over square root n. Okay, so we did it. We came up with the 95% confidence interval for the population mean mu. Okay, now we don't actually have values yet. All right, we want to get the actual upper bound, lower bound values. So let's look at this example. 95% confidence for mu, the true mean by state tuition. So here's the sample that I have on the Collaborate activity sheet. X bar is 21,994. Sample size is 5. That population standard deviation sigma is 5,460. So if I calculate the upper and lower bound, I am going to take the mean value of 21,994, add and subtract to it 1.96 times sigma, which is, in this case, 5460, divided by the square root of n, so the square root of 5. So the interval goes from $17,208 for the lower bound and up to an upper bound of $26,780. So remembering what a confidence interval tells us, there is a 95% probability that the true mean by state tuition is in between 17,208 and 26,780. There are a couple other measures that we want to look at with confidence interval. One is the margin of error. The margin of error, actually let me go back down here a little bit, is this piece that we add and subtract to the sample mean. Okay, we can think of that as what we are adding, that's the margin that we're adding and subtracting to that sample mean to take into account the fact that the sample mean isn't going to exactly estimate the population mean. So this is that margin that we add to that sample mean to account for the error in the sampling process. So the margin of error is, in this case, it's going to be, if we multiply just that piece out before we add and subtract it, that margin of error is 4,786. Okay, it's that piece that we add or subtract. So it's 1.96 times 5460 over square root 5. So, okay, now the width is just the difference between the upper bound and the lower bound. There's another way to get at that, and because the width is, or because we're just adding and subtracting the margin of error from the sample mean, we can also just take 2 times the margin of error to get the width of the interval. All right, so in this case, 2 times 4786, we get a width of 9,572. Okay, we've done just now one example of a confidence interval. The calculation is not complicated, and as you do more practice, it'll become pretty simple. What's more important to understand is, well, what does the confidence interval mean and how do we interpret it? So I've got two wordings of an interpretation here, and you can use whatever one makes the most sense to you. So one way to talk about it, a confidence interval, is to say that there is a 95% probability or chance that the confidence interval, and we're talking about the one we just calculated, the confidence interval from 17,208 to 26,780 contains the true mean by state tuition. The key piece of this is this probability word is associated with the confidence interval, and this got split up here. Probability is associated with the confidence interval because the confidence interval depends on that sample mean, which is random. It changes from sample to sample. We can only talk about probability related to random things. So the 95% probability is associated with the interval, not the true population mean. The true population mean is a fixed value. Even though we don't know what it is, it's not random. It is some fixed value. So the probability has to do with the confidence interval. All right. In other words, the upper bound and the lower bound values. Okay, another way to interpret a confidence interval is to say that we are 95% confident, actually use that word confident, that the interval from, in this case, 17,208 to 26,780 includes the true mean by state tuition. Okay, again, we want to associate that the confidence is in the interval. So we're 95% confident that that interval was calculated correctly in such a way that it includes the true mean by state tuition. So when you're asked to interpret a confidence interval, you can use these two wordings as a template to do that. Includes the true mean by state tuition. So that wording looks and uses the word confidence. And okay, let's look at this note here. So you notice we've gone from a point estimate of the sample mean, x bar, this one single value, to an interval in our attempt to estimate the population mean. So we're losing something in doing that, right? We're going from one single value to this interval of values. And from what we saw, it was a pretty big interval. It was like almost $10,000 from the lower bound to the upper bound in our example. So what we're losing is precision. And we are losing that, but what we gain is confidence. We now have a way to measure how reliable our estimate is. So we lose the precision, but we gain confidence in the estimate, and we gain a measure of reliability. And we're measuring how reliable the estimate is of the mean. Okay, so this brings us to part 2 of the collaborate activity. So you can go back to the sheet and calculate the upper bound and lower bound for your sample mean. You can use the example that I've done as a model to follow. You're going to use that same Standard deviation 5460, and you'll use that 1.96 and a sample size of 5. All right, so go ahead and do that, and hopefully others will be doing that as well, and you can compare your confidence interval with others' confidence intervals. You'll see that your upper bound and lower bound will show up on the scatter chart, and the population mean is in there, and you can see if your confidence interval includes the true population mean or not.